All right, so today we'll be talking about the language of quantum mechanics, and in order to convey richer ideas, you need a richer language. That is in general true for day-to-day communication, but also it is true for scientific communication. Not only communication, we also think in terms of a language. So whenever we think, you will notice that we are always thinking either through your mother tongue or on the basis of English or some vehicle. And that's also true for science. That means in order to do science, we have to adopt that particular linguistic medium that is suitable for that kind of science. And quantum mechanics has developed its own language, its own notational system. And that is what I'll introduce today. I was in the last two classes, I was talking about certain things which are not definitely the entire thing that you have done in the last semester. I was sort of focusing deliberately on certain things. I gave you a tutorial problem with that objective to point out that there is a sort of unifying theme running through quantum mechanics, and that is what we need to capture in terms of a proper language. Otherwise, what happens, probably the last year you have noticed, sometimes you will need to do a long calculations, long integrals and things like that, which might not really be necessary. The last class I illustrated one case where you really don't need to integrate. You simply see how things operate on each other and figure out that some things will be 1 or some things will be 0. To do all these complex integrations. And this brings a lot of economy, not only of writing, but also of thought. So let us start by just recapitulating what these unifying things were. For example, now again, I'm not talking about a particular kind of potential function. You have come across the infinite square well, the finite square well, the harmonic oscillator well. You could think of anything, but always the structure is that you start with a certain wave function, and that wave function, let me switch on the presentation now. Yes. The wave function at the initial time psi x comma 0 is given as a linear combination of the eigenfunctions, energy eigenfunctions. So these are I is equal to 0 to infinity. We can also put it 1 to infinity, depending on what we call 0 or 1. Ci psi I x. This is always true. So we essentially decompose the initial wave function into the component eigenfunctions. And then we say that psi x and t, as time progresses, it will be C1 psi 1 xt plus C2 psi 2 xt, and so on and so forth. And these are essentially, these will be composed of psi I x times the phase factor e to the power minus I e I t by h cross. But we can presently consider these as the way the second eigenfunction evolves. This is the way the first eigenfunction evolves, and the final evolution of the wave function is a linear combination of them. This is something that is true for all the things that you have studied. And what is the relationship between these? These are related by minus infinity to infinity psi I psi star x psi j x dx. If you have this, then this is equal to the delta function. This implies that these energy eigenfunctions are orthonormal to each other. This is something that you have learned. And since any given wave function can be decomposed in terms of these energy eigenfunctions, these form a complete set. There are infinity of them, and they form a complete set in the sense that any decomposed in their terms, right? Now, let us take this and let us multiply that by psi j and integrate. So let me first write what it was: psi x comma 0. I will multiply that by psi j star x. So this was integral of I is equal to 0 to infinity. It was Ci, then I have to multiply by that. So it will be psi j star x psi I x. Now I integrate. So I put an integral here. This will be minus infinity to infinity integral. And therefore here also I need to integrate. Okay, so what I've done is essentially I've taken this equation, I have multiplied by the psi j star, both sides, and I have multiplied them, I've integrated them. Now by orthonormality, so since they're orthonormal, then we get minus infinity to infinity, this guy here, psi j star, and put, sorry, x psi this then becomes 0 to infinity Ci, but this is something that you know. This is delta j. So this will be delta ji. And then this will kill off all the terms where I and j are not equal, and therefore that will simply lead to. So this is the overlap integral we had talked about, and it is the overlap integral that extracts Cj. I noticed that some of you were having difficulty in getting this in the tutorial, so I just wrote it up how you get it. So the coefficients are essentially obtained as an overlap integral between the different energy eigenfunctions and the given wave function. All right. Is sort of a unifying theme that runs through quantum mechanics. Even in the case of free particle, These were not discrete ones, but effectively the same theme is followed. It is a continuous set of eigenfunctions, but nevertheless, the theme essentially remains the same. Now, while you notice this, let me, okay. Scientists noticed that this theme has a uncanny resemblance to the way vectors behave. For example, if you take any set of vectors, suppose there is any set of vectors, v1, v2, v3, and all that, uh, and a set of real constants. This will be, say, a1, a2, a3, and all that. So any set of vectors and a set of real constants can form another vector. So v can be expressed as a1 v1 plus a2 v2 plus a3 v3. So you notice that these are the vectors, these are numbers put together also give another vector. Okay. So this is similar to what we had written there. So these are eigen, what should I say, individual eigenfunctions, and they put together give another wave function. So wave functions and eigenfunctions sort of appear to be behaving like vectors. This is, say, our first observation. The second observation is that you can always define coordinates, say, so suppose this one is, say, E1, this one is, say, E2, this one is, say, E3. So I can define a coordinate system like this. And if you have defined this, then this E's are, if it's to act as a coordinate system, it has to have the character that EI dot product with EJ has to be delta IJ. If this is true, then that acts as a coordinate system. And notice that this is similar to what we wrote here. So there are similarities between the way wave functions and eigenfunctions behave, and the way vectors are behaving. Now, if we have defined basis vectors, then the basis vectors form a complete set. Complete set means any vector v can be expressed in terms of, say, a coefficient v1 e1 plus v2 e2 plus dot dot dot, it would be, so all that put together. I'm not only considering a three-dimensional space, but if you have a large number of vectors, then this is essentially equal to, or okay, let's for now focus on only three variables. So it will be v3 e3, then it will be I is equal to 1 to 3. It is just vi ei And notice that this is similar to what we wrote here. So these are the bases, and I am expressing stuff in terms of that. So and then if I have a particular, say, vector, say V, I can find the components along E1, E2, and E3. How do we find the components along E1, E2, and E3? The components are found by the jth component is found by the scalar product. Huh? Let me get some space. Yeah. By the scalar product, it is Ej dot P. That will be I is equal to 1 to 3. It will be Vi. I mean, this is expressed like this. And then it will be Ej dot Ei, which is nothing but integral I is equal to 1 to 3 Vi delta Ji is equal to simply Vj. So that this is also similar to what we did here. So what I'm trying to point out is that scientists noticed that the behavior of the wave functions and the eigenfunctions, they are quite similar to the behavior of vectors. Many scientists noticed that. But for the first time, the scientist who put that into a proper formalism, proper notational structure, was Dirac. So that is what we will be talking about today. So I need some space, so let me delete this and let me delete this part and keep the upper part. Sorry. All right. Dirac said that since the wave functions are behaving like vectors, let us not fool ourselves. Let's just call them vectors. Call them vectors, but with a slightly different notation, because these are elements. We have to keep in mind that these are actually functions, and therefore these are members of what I would now call as a function space. That means these are functions. These are normalizable functions. Not only just functions, these are normalizable functions, which means that they're, they don't go to infinity at any place. And then the standard notation that he introduced is that if you have the psi n, the nth eigenfunction, then to represent that in the vector form, we'll put this. This is called the ket or ket vector. So whenever we put it in this notation, we have in our mind that this has a behavior similar to a vector. And we'll see further how. But let us talk about the notation. So if we have to represent the nth eigenfunction, we will put a vector notation like this. This is called a ket vector. Now, the advantage of this notation is that what you put inside doesn't really matter, so long as it conveys to the reader what it's supposed to convey. So you don't really need to write psi n. For example, you might say that this is nothing but the eigenfunction related to the nth eigenvalue, which is En. So this is same as, say, you write En, the same thing. Because the moment you write En, the reader understands that actually you are talking about the vector, about the function, eigenfunction, related to the nth eigenvalue. You can also write simply as this, because that also conveys the same thing. You can also write things inside. For example, if you want to convey that I'm talking about the ground state, you might write even ground state. So long as it conveys the idea to the reader, it's done. The ground state can also be represented simply by writing this. So all these are okay. All these are fine. So this is or you can also write even the ground state as, say, that's also fine. I mean, so long as it conveys what you want to convey, it's okay. Only thing is that we do not write, it's like this. So psi n, this is not how we write it. We do not put what it depends on, that we don't write for the sake of brevity. So these are then called the state vectors. So this is something that we will not write, therefore I will not keep it here to confuse you. So these are the state vectors. Now, if we can define state vectors like these, then we can also define the state psi, the wave function as a vector, as a1, psi1. I'll not put the small psi because now I'm talking about the time dependent things. So I'll just put it as capital. So it's psi1 plus a2 psi2 plus ... So this is a way we can write it, because these also form a complete set of basis vectors. The way we wrote a vector in terms of a set of basis vectors, we are writing these as a set of basis vectors. So now our thought has gone into thinking of these not as functions, but also as vectors. So this is nothing but the idea of vector addition. Now let us talk about the inner product. Of two such vectors, f and g. Now this inner product is written in the form f, this is called a bracket. So this inner product will then be our well-known concept of the overlap integral, f star x g x. So whatever this was the overlap integral between f and g. That is the same as the inner product of the two vectors. So this is a shorthand, small, compact notation for this integral. And you will see this has a lot of advantages, because now we will be able to manipulate these kind of things to ultimately avoid doing integration at every stage. But yes, ultimately, when we have to compute this, we'll have to integrate this. That's fine. For example, look at the economy of notation. Suppose we are talking, you have already done in the last year, the 3D picture. In that case, there are two vectors in 3D. It would be f Then it is minus infinity to infinity, minus infinity to infinity, three integrals, minus infinity to infinity. It will be f star x, y, z, and g x, y, z, dx, dy, dz. All this thing is simply represented by this. The moment we know that f is something three-dimensional, g is something three-dimensional, we know that this is how we write stuff. Okay, so this results in a great compactification of our notation, and so the amount of writing that we will have to do on board will be much smaller than what we were doing so far. So now then, I need some more space, but I do not have. So let me see how much I can write here. So then psi this equation, let me write in terms of let me write this equation in terms of the Dirac notation. Let me write this equation in terms of Dirac notation. It will be I is equal to 1 to infinity Ci psi I. That's it. So it is a lot of a compact notation. Let me write here itself. Then we know whenever there are two such things which are orthogonal to each other, so we can write psi I, psi j, this will be delta ij. So this is just an inner product of the ith and the jth eigenfunctions, and that gives the delta ij. This is similar to what we wrote here. So this will now express only as such a shorthand notation. Then if you have the overlap between an eigenfunction and the wave function, what we will write is psi j, and the capital psi is the wave function. We are trying to find the overlap integral between the capital psi and the jth eigenfunction. With that, psi is expressed as this, and therefore we will put it here. It will be I is equal to 1 to infinity here. It will be Ci comes to the front, and then it will be psi j, it will be psi I. This is what you are putting here. So this is clearly this will remain, and this is delta ij. So it will be I is equal to 1 to infinity. This is Ci delta ij is equal to Cj. Exactly what we did there. Okay. So essentially we are talking about great economy of notation. We will simply write this to mean the whole bit of overlap integral as here. And we will extract the coefficient this way, and we will now extract the coefficient this way. You might ask, is the function space in every respect the same as the vector space? No, not really. Because the Dirac bracket like this can also be complex. So that is one important difference. The Dirac bracket might also lead to a complex number, while that doesn't happen in the real vector space, real value vector space. The other thing is that this kind of expressions, these might lead to infinite number of terms, which means that the basis vectors, in case of a vector space the way I drew, there are three vectors in terms of which every vector could be represented. In this case, that could be infinite dimensional. There could be an infinite number of discrete vectors like this, and that would be needed, but still, nevertheless, that infinite dimensional vector space would be complete in the sense that any vector can be expressed in form of like this. So let me again delete this part, otherwise I'll not have space to write. I need to delete this part.
So,
Yeah.
can you please explain why are we considering the wave function as a vector?
Because it has characters similar to a vector. There are, in a vector space, there can be basis vectors in terms of which any vector can be expressed. In the function space, there are basis functions in terms of which any function can be expressed. You can have ideas of adding vectors. You can have ideas of adding functions. You have the idea of a dot product between two vectors. You will have the idea of similar inner product between two functions, and so on and so on. The question, because of these similarities, scientists found that it is convenient to think of functions as vectors.
So, can you explain the possibility of infinite dimensional vector space, the last point which you mentioned?
Infinite dimension, for example, if you have already studied the harmonic oscillator situation, there you know how many of the eigenfunctions are there, how many eigenvalues are there. Actually, infinity, right? They are equally spaced in case of the harmonic oscillator, but there are infinity of them. And any initial wave function can be expressed in terms of them, and the space is actually infinite dimensional because there are infinity of such eigenfunctions.
Okay, thank you, sir.
Any other question? What is the actual difference between capital psi and small psi? Okay. Capital psi I'm using when I that wave function, and small psi I'm using as a solution of the time independent Schrodinger equation. Therefore, the small psi's are not time dependent. Okay, so wherever I'm talking about the time independent eigenfunctions, these represent a small psi, and whenever I'm using time dependent, I'm using that as capital psi. Now, the norm of a vector, the magnitude of a vector. Okay, of a vector. How do you calculate that? Say the magnitude A is basically the magnitude of the vector A. This is, if you recall, calculated as A dot, right? And this turns out to be A1 square plus A2 square. And this is real and non-negative. So this is the idea of a magnitude of a vector that you had learned. Can we port that in the function space? Can we talk about the magnitude of a function? Yes, we can do that by considering this. A function f, its bracket with itself. This is nothing but minus infinity to infinity. This is F. Right? And this is simply minus infinity to infinity. This is fx square. And this is its norm. This is obviously real and non-negative. Okay. So the magnitude of a vector was calculated this way. A magnitude of a function we can calculate this way. That means it is a bracket with itself. So the norm.
So aren't we missing a root there?
Again?
Aren't we missing a root?
Are we missing? Well,
Like under roots.
Sir, she is saying that if inner product is the norm squared, right? So.
Oh, that has to be root. Yes, yes, agreed. So it has to be a root of that. Yes. So the norm of f will be this is f root of that. That's what you said. Yes, it's right. F and f, its bracket is this, and the norm of f is this. Okay, you are right. So this is. Then if the norm of f turns out to be 1, we call that function as normalized. Right? So that is the idea of normalization. Itself is not the norm. Yes, you're right. The square root is the norm. Then I need to again clear off stuff. Let me delete this. Now there is a obvious inequality that ordinary vectors obey. Vector like this and another vector like that. Say this is our A vector and this is our B vector. And therefore, the projection will be this. Okay? Now this picture makes it obvious that the inequality A dot A and B dot B, so these are the two dots, must be bigger than A, right? So this, its magnitude times its magnitude definitely is bigger than the projection's magnitude. So, and if this is true in the vector space, in the function space, its equivalent is to write something like this. Should be bigger than okay. This is actually an extremely important inequality which we will use in deriving the uncertainty principle. It's called the Cauchy-Schwarz inequality. Okay. So keep it written in your copy because we will refer to that later. And this is obvious that this will be true by the construction. I'll not go into the detailed mathematical proof of it. Intuitively, this should be true. Now, if we have a situation where this equal to 0, then what do we say? We say they are orthogonal. And in order to call it orthonormal, their individual magnitudes have to be unity. For example, for the harmonic oscillator, our psi was I is equal to 1 to infinity. I'm writing again because I've deleted that. Ci. Okay. This is the at the initial time. This is so. Now, if this is what shows that since this is true for the harmonic oscillator, these form the basis set, and a collection of these terms, the linear combination of the basis set, gives the wave function. And these are the complete set of basis vectors. Huh? Now, the point that I'm trying to drive home before we end today is that this is not the only way that this can be expanded. If you choose a different basis, then it can be expanded in the same way, so long as that basis is also a complete basis, right? So the choice of basis is not unique. Choice of basis is not unique. You can have different basis. Let me kill this and I want to show what I mean to say. Suppose I have, let me draw here. I have two basis vectors like this. So this is our psi1 and this is our psi2. Okay, and a vector psi is expressed in terms of these two. We can always do that, and you'll see that we can draw projections, and these projections are nothing but the overlap integrals. How big is this? Overlap integral. How big is that? The overlap integral. So overlap integral between psi and psi1 is this projection. The overlap integral between psi and psi2 is this projection, and so on and so forth. So you can find out C1, C2 this way. Okay, but that does not prevent you. Let me choose another color and do that. That doesn't prevent you from defining another set of vectors like this, so long as these two are also orthogonal to each other. Let us call it, say, phi phi1 and phi2. Here also we can drop perpendiculars and find out its component, and thereby I can express the psi in terms of the phi1 and phi2. So you can easily see in this picture, the choice of the basis vector is not unique. If you have a particular function psi and express in terms of the psi1 and psi2, you can always define another basis phi1 and phi2 and express it in terms of them, right? So this is an important factor that we'll consider, because you have learned in the last semester that the psi function represents the complete information about the system. Complete information means you would like to know the information about the position, you would like to know the momentum, you would like to know the information about energy, and so on and so forth. All that information is contained. Now, depending on the coordinate system you choose, the basis you choose, you can extract each of this information. If you choose the energy basis, you extract the information about the probability of finding particular energy values. If you choose the basis of position, you extract the information about the probability of finding definite position values, and so on and so forth. So this basis, choice of basis, is a very important thing in quantum mechanics. So today my time is up, so I'll finish by just pointing out that the choice of basis is not unique. The choice of basis is not unique. You can, for your own advantage, choose different bases, and then the projections will be different. And therefore, the overlap integrals value, the magnitude that you extract out of the overlap integrals will be different. But then this is a way that you will choose in order to extract various information out of a single number psi. Okay, let's finish the class today. Have any question? There's 1 minute yet.
Yeah, sir. So I have a question.
Yes.
Yeah.
Welcome.
So while introducing the bracket notation, you mentioned about the inner product. You said that the inner product can also be a complex value. So
Yes.
in this regard, in the current example, we see that they represent the overlap integral sort of represents the inner product sort of represents the overlap integral, the constant C1 C2 that we can see here. So what would that mean in if we get a complex number?
Yeah, constant C1, C2 are complex.
Result of it.
Yes, the numbers C1, C2, these are not real numbers. These are complex numbers.
Oh, okay, sir.
Okay, these are numbers, but complex numbers. In general, complex numbers. Somebody asked, is the Hilbert space another name for function space? I have not yet used the word Hilbert space because there is a bit of twist in that. I will come to in one of the later classes. Presently, I have defined the function space as whose elements are functions that are normalizable. That means whose norm is finite. The moment the norm is finite, you can obtain the norm and divide the function by that to normalize it. So effectively, I have confined myself to that. But Hilbert space encompasses a little more. And that is why I have not yet called it Hilbert space, because that will not be mathematically right. I'll come to that a little later. Any other question?
Sir, here the overlap is psi or psi on the psi 2.
Overlap is overlap between F and G is integral of x star G dx. So if you want to calculate the overlap of your function, the function that you are starting with one of the eigenfunctions, say psi 1, so it is integral of psi 1 times psi dx.
Okay.
I've written that a number of times. If you revisit the lecture, you'll see I've written the overlap integral a number of times. If you want that, I can just quickly write. So the psi I psi, this is the overlap integral between the two, is minus infinity to infinity psi I star psi. That's it. Okay. This star actually guarantees that if you take the same thing, then you get the norm. That's all. Okay. Because these are all in general complex numbers, so you need to put a psi star there. Any other question? Okay, let's call it a day today, because if you have any questions, no problem. Ask the next day. I'll be there. Okay. During the weekend, do solve the tutorial problem, and let's meet next week again. Time is up. Let's finish.